Okay. So, good morning, good afternoon, and good evening to all of you. It's with a great pleasure that I warmly welcome to the 7th webinar of our Resilience Catalyst talk series. Just to present myself, I'm Petra Malizam from the UNESCO Chair on Intersectoral Safety for Disaster Risk Reduction and Resilience at the University of Udine. And I'm giving this short introduction as I am with the Chairholder, Professor Stefano Grimatz, and our collaborator, Lucille Anglais, one of the coordinators of the Resilience Catalyst initiatives. What is this initiative? It is born under the umbrella of UNESCO, and it's an initiative part of the Resilience Program that is a program supported by the Central European Initiative. The goal of this initiative is starting to exploring the role of the UNESCO chairs that are focused on disaster risk reduction and resilience in order to consider how we deal and how we cope with the complex situation of our normality and the interplay between the UNESCO pillars of education, science, and culture, with the goal of transforming the governance for building resilience to disasters. So we had an initial collegial meeting 1 year ago that where we launched this talk series where we intend to showcase the works and activities of the different UNESCO chairs focused on disaster risk reduction and resilience. Just to have a sum up of what we have done so far, we had the other 6 insightful sections. The first was dealt by the UNESCO Chair on Disaster Risk Reduction and Resilience Engineering, led by Professor Dina Dayala at the University College of London. The second from Professor Tachikawa, glad to have you here, the UNESCO Chair on Water, Energy and Disaster Management for Sustainable Development, Wendy, at Kyoto University. Then we had the UNESCO Chair on Water-Related Disaster Risk Reduction at the Ljubljana University in Slovenia, led by Professor Mikoš. The UNESCO Chair in Informatics and Multi-Hazard Risk Reduction at the Loughborough University in the United Kingdom, led by Professor Liang Kiha. The UNESCO Chair on Urban Resilience, sorry, now I'm reading because I will forgot someone for sure. The UNESCO Chair on Urban Resilience, led by Professor Tolling in southern Denmark. And last month, we had the UNESCO Chair in Cultural Heritage Management and Sustainability at the University of Pannonia in Hungary, led by Professor Mislevitz. So we had all these talks where each chair presented their activities, and we ended with a final discussion that I think is the same program of the meeting of today. And for your information, all the recordings of these sessions are available on the Resilience Catalyst webpage. You will find the link in the chat. And also, if you join us on Facebook and LinkedIn, you can find and you receive information on these events timely. So for today, we are really honored to welcome the esteemed colleagues from the UNESCO Chair on Prevention and Sustainable Management of Geo-hydrological Hazards at the University of Florence in Italy. The UNESCO Chair is chaired by Professor Nicola Casagli, and we have here today the co-chairs Tofani and Castelli. It's really a pleasure. And the presentation of today will deal with risk assessment and early warning for community resilience. That is a key topic of interest of many UNESCO chairs within our initiative. We extend our sincere gratitude both to all the speakers, Professor Tofani, Castelli, Bianchini, and Arrighi. Thank you really for organizing this insightful session of the main activities. And I think that you reserved a discussion moment at the end of the meeting, or you can say how you are organized for the meeting of today. So without any further delay, I give you the floor to you, esteemed presenters. Thank you.
Thank you. Thank you, Petra. Good morning, good afternoon to everyone. Thanks for the invitation to this relevant initiative. I'm going to share the screen. Can you see my screen, my presentation?
Yes.
Yes.
Okay, good. First of all, I will briefly introduce myself. I am Veronica Tofani, Associate Professor of Engineering Geology at the Department of Earth Sciences of the University of Florence and Deputy Chairholder of the UNESCO Chair on Prevention and Sustainable Management of Geo-hydrological Hazards. Before going to detail in my scientific presentation, I would like to say a few words about the UNESCO Chair, which was established in Florence in 2016 with the mission of the chair is to promote research and development for the prevention and management of geo-hydrological hazards, mainly floods and landslides, in order to support policies and actions of risk reduction. The UNESCO Chair has 4 main objectives, which are developed. The first one is on research and innovation. So develop research and innovation for the prevention of and mitigation of geo-hydrological hazards. The second one is support the policies for risk reduction and resilience enhancement. The third one is related to cultural heritage, to protection of cultural heritage treated by geo-hydrological hazards. And the fourth is promote scientific networking, open science, and capacity development. As already mentioned by Petra, the chairholder is Professor Nicola Casalli, full professor of engineering geology at University of Florence. Then we are 2 deputy chairholder, me and Professor Fabio Castelli, who will talk later and introduce himself. And then 3 program coordinator, Professor Silvia Bianchini, which is program coordinator for science, will deliver her talk later, and Professor Enrica Caporali, which is program coordinator for education, and Professor Chiara Arrighi, who as well will talk later, which is program coordinator for engineering. We have a total staff of more than 100 senior and early career researchers. Today's talk is entitled Risk Assessment and Early Warning for Community Resilience. We have 4 presentations. The first one is given by me, is related to artificial intelligence for landslide hazard risk assessment. The second one will be delivered by Professor Bianchini on landslide early warning system and monitoring strategies for risk management. The third by Professor Fabio Castelli, which is related to early warning for floods. And the last one by Professor Chiara Arrighi on community participation for flood risk assessment of art cities. So going back to my presentation, to the contents, I will give a brief introduction about landslide risk assessment framework, and then I will talk about a case study, which is related to the case studies in Italy, in the central part of Italy, where we performed a quantitative risk assessment for landslide, and starting from susceptibility assessment, intensity assessment, vulnerability and exposure assessment, and at the end, quantitative assessment. So the need to have quantitative landslide risk assessment map is coming. So the motivation of our work is coming also for international policies. As you may know, the Sendai framework for disaster risk reduction is structured into 4 priorities for action. The first one is related to understanding disaster risk and mention clearly how is the necessity to have vulnerability, exposure, and hazard map in order to prevent, mitigate, and respond to disaster risk. Dealing with landslide, another important international commitment is the Kyoto Landslide Commitment, which is commitment to the Sendai framework and for global promotion of understanding and reducing landslide disaster risk. This commitment was signed by more than 100 signatories, including UNESCO, World Meteorological Organization, UNDRR, and United Nations University. And like the Sendai framework, is structured in priority action, among which we have at the second point, hazard vulnerability and risk map assess and risk map for landslides. Another motivation is related to the cost of landslide disaster. According to the international disaster database provided by the Center for Research and Epidemiology of Disaster, which published a few years ago together with NDRR a book summary which is entitled Human Cost of Disaster, we can see that the number of landslide disasters are increasing in the last year, together with the total death and the total damage, economic losses due to the occurrence of landslides. According to the Barnes, let's say, definition, risk in general and also for landslides is defined as the expected number of lives lost, person injured, damage to properties, disruption of economic activity due to a particular phenomenon for a given area and a reference period. So landslide risk is the product of landslide hazard, vulnerability, and the exposure. So when you assess landslide risk, you have to answer to multiple questions. First, you have to answer where, when, and how large a landslide will be, and this is the probability of occurrence hazard. Then you have to answer what destructiveness the landslide will cause, and this is the landslide intensity, which is a component of the vulnerability. Then you have to answer to the question if an element of risk will be affected or not. If yes, you have to define vulnerability, so the degree of loss of an element at risk, and you have to define also the exposure. When you define the probability of occurrence, in many cases, you don't have enough information to define when a landslide will occur. So in some cases, you use susceptibility as a proxy of hazard. Susceptibility is the spatial probability of occurrence, so where a landslide will occur. In machine learning and machine learning and deep learning application are a subset of artificial intelligence, which mainly, as you may know, relate to the development of algorithms that learn from and make decision based on data. Recent studies have demonstrated the effectiveness of the use of machine learning and deep learning approach in landslide research. Especially the application of machine learning and deep learning are related to landslide detection and mapping, landslide spatial forecasting, so where landslide will occur, which is the susceptibility, as we have just mentioned, and also is used for intensity mapping. And machine learning, and deep learning application are also used for landslide temporal forecasting. We, as UNESCO Chair, we have been working since many years on landslide risk assessment. This is one of our recent work related to the Europe, which is published in Review of Geophysics, in which we have assessed landslide risk for the whole Europe, starting from susceptibility assessment, exposure, and then the total risk is the product of susceptibility exposure, assuming that vulnerability is equal to 1, since we didn't have enough information to assess vulnerability at European scale. Now I'm going to present a case study, a local case study in Italy, in which we computed from a quantitative point of view landslide risk for a catchment in central Italy, starting from the assessment of susceptibility, vulnerability, and eventually the risk. This catchment is located in Marche region, in the central part of Italy, as an extension of 380 square kilometers. And in this catchment, in 2022, an intense rainfall event with precipitation of more than 200 millimeters in 12 hours triggered more than 800 landslides. These landslides were inventorized thanks to the use of optical images through a procedure called change detection, using images pre and post event, and more than 800 landslides were mapped, mainly shallow, fast landslides, which are very small in dimension, have an average landslide extension of 600 square meters. These landslides were the starting point for the evaluation of landslide risk. So our mapping unit is our slope units, which are portion of slope with uniform geomorphological and morphological condition. Then we apply machine learning approaches for landslide susceptibility and intensity assessment. We quantify the vulnerability, and then we assess risk in terms of expected economic losses for buildings. The first step was the susceptibility assessment, applying a machine learning approach. The goal of the machine learning models is to statistically analyze the relationship between a set of predisposing factors and the occurrence of past landslides. The model that has learned this relationship, so the optimal configuration of the model, is employed to predict where areas may be unstable. Results are presented in terms of probability of landslide occurrence, so values from 0 to 1. The input data of this model are the so-called dependent variables, so the presence or absence of landslides, which in this case it is the landslide inventory realized after the event, while the independent variables are the so-called predisposing factors, which are a list of geological, geomorphological factors which are contributing to the spatial occurrence of landslides. In this application, we have used a machine learning approach, which is called explainable boosting machine, which is a class of machine learning model designed to combine high interpretability with the strong predictive performance. The predisposing factors, the predictor, represent geomorphological, geological, land use, soil and meteorological properties, which are used to assess the landslide susceptibility. This is the final map, landslide susceptibility map, which the values go from 0, no susceptibility, to 1, highest susceptibility. So it's a range of value providing the information related to the spatial probability of occurrence of landslides. I would like to highlight that this map has been realized, for shallow landslides, for landslides mapped within the inventory after the event. Then we have assessed landslide intensity, which is being defined as a function of landslide area and velocity. Intensity has been estimated in quantitative terms through a machine learning approach, and the observed landslide area is the dependent variable in this case, while the geomorphological parameters are used as independent variables. So the model the machine learning model predict the estimating landslide area, starting from the observed extension, landslide extension, and a list of geomorphological parameters. On the right, you have the final map of the estimated landslide area. Moving from purple to yellow, increase the estimated predicted landslide area. This is the velocity assessment. For mapped landslides, the velocity has been estimated using the AIM method, which is a method based on the energy line, so the evaluation of the kinetic energy along the path of the landslides. And then again, we have estimated velocity outside mapped landslides using a machine learning approach where the observed landslide velocity is the dependent variable and the geomorphological parameter are the independent variables. Velocity and predicted velocity and predicted extensions have been combined in order to define the landslide intensity, which has been normalized from 0 to 1. This is the final map of intensity, where you have yellow is meaning that is expected in higher velocity, when you have blue is expected a lower, a lower intensity. Then the intensity has been used to define the vulnerability. Vulnerability has been assessed as a function of landslide intensity and structural resistance. The structural resistance is computed using resistance factors coming from the defined on the basis of the input data coming from the ISTA census sections, where we derived information about the building related to the type of foundation, state of maintenance, number of floors. So we define per each slope unit the resistance value, the structural resistance value. Then we combine with the intensity and the vulnerability following the approach proposed by Lee and Etali. The vulnerability is quantified as the function of the ratio between the intensity and the resistor. On the right, you have the vulnerability final map for buildings. In yellow, you have portion of the basin where you have higher vulnerability, meaning that you expect to have the higher degree of losses due to the related to buildings due to the occurrence of landslides. Eventually, we combined the susceptibility, the vulnerability as a function of the intensity, and the exposure, which is the exposure in this case is expressed in monetary terms, considering the spatial distribution of the buildings from the OpenStreetMap database and the market values, derived from a data set managed by the National Revenue Agency of Italy. So we combine susceptibility, vulnerability, and the exposure, so the value of the elements at risk, and we define the risk, the expected economic losses for the catchment. And in the right, you have the final map of risk, which is expressed in euro per square meters. In red, you have the areas with the higher expected losses, economic losses. In purple, the area with lower economic losses. We computed a value, we estimated a value of economic losses, a sum of economic losses in the catchment of 22 million euros. Related to is the sum of the expected losses for the catchment. So this is the last map in the end. So thanks for the attention, and I've been a little bit longer than expected. But if we have any question, I will be. I stop my presentation. I will be glad to answer at the end after the presentation of my colleagues. So the second one is Silvia Bianchini.
Yes, can you hear me?
Yes.
Yes, yes.
Okay, hello everyone. I am going to share my screen. Okay, thank you again also from my side about this opportunity. My presentation deals with the landslide early warning system and monitoring strategies for risk management. So here there is a short table of contents. I will talk about monitoring and early warning system at regional and local scale. And finally, I will address these monitoring strategies within the framework of landslide risk management. So first of all, what does landslide monitoring mean? It is the quantitative measure of one or more variables related to the landslide evolution over time through the use of suitable instrumentation. Well, monitoring of a landslide can be a surface or a deep monitoring. In this short talk, I will only talk about surface monitoring that can be performed by means of traditional methods or remote sensing methods. Here on the left, you can see a variety of instruments we can use. Sometimes the better solution is an integrated use of these approaches to basically to improve the data reliability. The purposes of a landslide surface monitoring is the definition of the spatial extent of the unstable area, to determine the deformation field, identify if there is a possible landslide widening, quantification of the displacement and its variation over time, identify paroxystic events, and basically define risk scenarios. Early warning, an early warning system of landslide can be defined as a method able to provide timely and effective information through identified institution, which allows exposed individuals to avoid or reduce their risk to themselves. This is a definition provided by the present United Nations Office for Disaster Risk Reduction. And it is basically a matter of controlling and potentially forecasting the landslide movement, in particular, for example, by using the movement itself, the displacement. So landslide usually has this kinematic behavior as a creep. And if the landslide starts to accelerate with a very abrupt acceleration, in this tertiary creep, this third stage, the velocity goes towards infinite with this hyperbolic acceleration. And the method to control and alert about the landslide behavior is to define empirical thresholds in this third stage. So if there is the creep acceleration, this graph on the right, we can consider that every part of this acceleration corresponds to a different level of risk. So for example, green is a normal ordinary safe situation, up to orange and red that is basically close to the failure. And so the empirical thresholds are defined on the basis of the recorded displacement and, for example, maximum velocity values that are recorded and correspond to a different status of the warning system, going from normal to warning and alarm. This is an example on a landslide in South Italy. And more in general, within the national Italian early warning system, this can be graphically presented as a situation you can see on the right, corresponding to different actions and also to different frequency of reporting, from weekly reports up to continuous updating of the data. The kinematic characteristics of landslides determine the applicability of different methods to monitor them. So according to the classification by after Crunden and Barnes 1996, the slow moving landslides that are the one that move some tens of centimeters per year, for example, can be detected by means of satellite interferometric approaches, while passing to faster phenomena, we can use, for instance, ground-based instruments like radar interferometers, thanks to the shorter revisiting time and the shorter microwave length radar signal. Fastest landslide can be investigated and monitored with on-site sensors. The spatial scale of analysis also influences a lot the type of monitoring we can implement. Overall, we can have a regional scale on wide areas, a mesoscale, for example, a basin, up to the scale of a single slope. An example of slow-moving landslide monitoring on a regional scale is nowadays implemented in Tuscany region in Italy, in central Italy, by exploiting satellite radar interferometric technique called persistent scatterers interferometry. I will show you briefly an example. This method, persistent scatterers interferometry, is a technique based on the analysis of SAR, synthetic aperture radar images, acquired by the satellite on the same area in different time, in right side looking, in ascending and descending orbits, to allow the measurement of movements with millimetric accuracy on radar target called persistent scatterers that are, for example, buildings, parts of a road, and so on. Basically, after the elaboration of the satellite image, we have a grid of PS, of persistent scatterers targets, classified according to the velocity along the satellite line of sight, and for each point, the temporal series of displacement. And nowadays, in Tuscany region, the availability of Sentinel-1 satellite image of the European Space Agency, with a very regular acquisition plan with 12 days of revisiting time on the same area. This constellation allows an innovative near real-time monitoring service called PS monitoring, persistent scatters monitoring. So it is a monitoring of the formational scenario at a regional scale, rather than solely mapping landslides. So this approach permits to pass from a static picture of the regional slope stability to a periodic updated movie of the scenario, with a systematic update following the revisiting time of the satellite and its systematic processing, useful, for example, for civil protection practices. Here there is the workflow of the PS monitoring service. So we start with the acquisition of the satellite image. We create ground deformation maps, and the time series of displacements of the points are identified automatically to identify any change in the deformation pattern higher than a threshold that is set at 10 millimeters per year. We want to identify if there is a velocity variation, for example, an acceleration that is important for early warning. And then there is the phase of radar interpretation, because there's anomalies, there's velocity variations are analyzed with the support of thematic information, for example, geomorphological maps, land use maps, optical images. So a possible triggering factor is assigned to each anomaly related, for example, to subsidence or slope instability, and so on. The monitoring system in Tuscany leads to the production of a monthly bulletin at municipality level. So each municipality is classified according to 4 color codes with respect to the increasing attention level. So green means that there is no anomaly, while the red color means that there is the presence of at least one velocity variation that is persistent and relevant, while where persistency means that is referred to the repeated occurrence of the same anomaly across time in the same area. And relevance means the interaction with the elements at risk, such as buildings and roads on the territory. And on this red, this red municipality, the operational protocol in Tuscany requires that this municipality that are in red in the bulletin, field surveys must be performed to validate the remote sensed data to better understand the causes of anomalies. So field surveys leads to a preliminary risk assessment, to suggestion of actions to be taken, that can also lead to collect financial funds for further in-depth investigation, for example, to perform a building damage level assessment, installation of other instruments, hydrological modeling, and so on. So the bulletin is the starting point for prioritize the intervention measures. And the second example I want to show you is on a rapid landslide. So a debris avalanche occurred on an important highway in Italy. And here a monitoring system was set up, and it included both remote sensing and on-site instruments. The landslide occurred in November 2019, started as a rotational sliding and then evolved into a rapid debris flow due to the high slope and the increasing water content. And the kinetic energy of the landslide led to the destruction of the viaduct pylons, and also the rotation of the roadway of an angle of 19 degrees, as you can see here in the photo. And a photogrammetric survey by drone was performed just after the event to retrieve the three-dimensional model of the involved morphology. And then a monitoring network was implemented, dedicated to both the structural monitoring of the road, of the viaduct, and the terminal part of the landslide. So the purpose was to verify the absence of any other any deterioration of the structure due to the impact of the material accumulated in the valley, and to promptly detect any other episodes of reactivation of the lower part of the landslide. So a pluviometric station was put here on the crown, 3 ground-based interferometers for the displacement and the structural monitoring, a robotized topographic station, and also 3 multiparametric columns for differential monitoring, equipped with inclinometer, accelerometric sensors, connected also with teletransmission for the management of the traffic on the highway. The pluviometric monitoring was based on data from 2 rain gauge stations installed nearby the landslide crown. And from the date of the installation, they recorded 2 significant rainfall events that exceeded the defined pre-alarm and alarm threshold on different cumulative time periods. And this is an overview of the ground-based radar interferometers installed. I want not to go in detail, but just highlight that here on 2 marked increases in displacement were recorded here that are exactly coincident with the 2 rainfall events we have seen before. So it confirms that the rainfall is the main factor controlling the deformation trend here. And other instruments for the displacement monitoring, I found the monitoring, the short range monitoring of the pylons of the structure. And finally, lastly, 3 detection system were installed on the body of the landslide, equipped with inclinometer and accelerometer sensors that detected any impact produced by the potential other passage of fast-moving material. And they were connected with an aggregator, a logic aggregator, connected to safety devices capable of blocking the motorway traffic, so connected to traffic light and to automatic barriers, and also an acoustic warning alert system. This is a table that shows that for each of these instruments, threshold values were set and correspond to different warning levels up to alarm. So the automatic instrumental threshold activate and deactivate the different operational phases and also actions to be taken. In particular, in this case, the management of the traffic on the highway, the highway closure, for example. Finally, to conclude, within the landslide risk management, we can say that the monitoring system of landslide can be included in the prevention phase for investigation and knowledge, for example, for retrieving kinematic parameters, so for the short and long-term control of the landslide evolution, but the monitoring system can also be implemented within the intervention and remediation phases. So as a non-structural measure, because the non-structural measure can correspond to the monitoring system itself, or a structural measure, so to, for example, to verify the effectiveness of the mitigation and stabilization works. And this is the very last slide to say that the early warning system and monitoring strategies can be thought as composed by 4 different components. The first component is the design, so gathering knowledge of what is available for the area of interest, where to set the early warning system, and so on. The second component is the monitoring, so to collect the data. The third one is the forecasting, data interpretation, comparison with the threshold. And finally, another fundamental part is education. So people must know what to do, otherwise they receive a message but do not know what to do. So we need to increase the risk perception and learn safe behavior and know how to react to a warning. So we need to involve the whole population. That's all. Thank you for your attention.
Okay, I guess it's my turn. Let me. You want to take a 2 minutes break, or we keep going? What do you say, Petra? We keep going. Okay.
Yes, I think you can.
There is a raised hand I see in the.
No. Sorry, I was going to put another thing. Sorry.
Okay, so let me share my screen. I'll just take a second. Let me do. Okay, can you see my screen?
Yes.
Okay, so let me first very quickly introduce myself. I'm Fabio Castelli. Besides being deputy chairholder of this chair, I'm also professor of hydrology and water infrastructure at the University of Florence. Well, I'm going to talk in very short presentation. I'll try also to save some time to leave room for questions. Is the research we are doing trying to answer an increasing demand towards impact-based early warning systems for floods in this case. So to better motivate this increasing need, let's take a quick look at what we intend by flood prediction, and in particular flood risk prediction. Okay, at the end, we are not really interested just in flood hazard prediction, but more in risk prediction. So it's traditionally hazard prediction in hydrological science is predicting the runoff and the river discharge and stage. When we are talking about risk prediction, we want to try to also predict in real time, that is to issue an early warning, what is the exposure, that is predicting which areas and what in those areas will be flooded, and more in general, also predicting in real time what are the vulnerability. In a broader sense, predicting what will happen. That is really what matters for decision makers. But current state of the art, these three different levels of warning are only, I would say, managed not continuously, and in reality, only in real time we have only prediction essentially of hazard, while prediction of exposure and vulnerability are routinely managed in what we call in deferred time through risk management plans or civil protection plans. So we have also a sort of not just separation of tools, but more importantly, separation of services and responsibility. And so we also need to address the limits and what are the criticalities of this sort of separation between operational services in an overall risk prediction. A notable example of the need to a better integration of the services is the dramatic event of Northern Europe 2021. On the left side, we have what was issued as classical flood hazard prediction, which was actually very accurate, okay? Beside being issued, as I will discuss if I have time later on, in a probabilistic term, but the high probability of having flooding on very, very large regions was issued very well 2 days in advance. Nonetheless, okay, more than 240 casualties have been reported, mainly in Germany and in Belgium. Okay, this is considered as a typical example of why we need actually to push the early warning, not just in terms of hydrologic prediction, but in impact prediction. And these and other events like this gave birth to the well-known UN initiative, which is called Early Warning for All, okay? Which is essentially devoted to bring early warning closer to both citizens and communities, I would say also closer also to decision maker, okay? So we have to work more on adapting forecasts to end user needs. And this also have would say a fallback on the design on the early warning itself. So what are the user needs to be considered a primary system configuration element and not just something that falls down along a prediction chain. So talking about flood predictions chain, this is more or less the standard probabilistic flood prediction chain. Probabilistic because there are still a lot of uncertainty to be resolved also on the physical processes. So we have essentially most systems are based on two links only on a prediction chain. We have a meteorological prediction where, when, how mass precipitation will occur. And of course, we have to deal with uncertainty in meteorological prediction due to convective cloud dynamics and so forth. And then the following link is the hydrologic prediction. How much river flow, okay? And also here we have uncertainty about sensitivity to soil moisture, land and river geometry, sparsity of monitoring network. So the decision makers is forced to deal with a probabilistic prediction, which is limited to the physical phenomena mainly, okay? And you have to confront this probabilistic prediction of hydrologic processes of flow river and eventual possible inundation, what is written in the further time analysis, for example, in civil protection plans, okay? And the main difficulty there that you have to take decision under larger uncertainty. And decision under uncertainty, theory of decision under uncertainty tells very well, require exploring not just the probability but of something to occur, but what is the utility of taking different decisions. And so to have this kind of evaluation, we need to add further link to the prediction chain. Okay, of course, on the physical process, we have to have a better prediction on what will be the flooded areas, okay, and more important, the capability to have real-time impact scenario, who, what, and how they will be affected. This is non-trivial because this also brings in further uncertainty that cannot be resolved fully in the further time. And measures of uncertainty are all the behavior of the anthropogenic components that go from the engineering part, including foam mitigation, measure how well they will be functioning during an event, but also which is the behavior of communities and citizens, whether a given part of the city is being interested by a specific event. All these factors and uncertainties that need to be also somehow evaluated in real time. So we are doing some research mainly now on this part of the new links of the chain, and our testbed is again a highlight, as also in previous presentation, the importance to address this cascade of process across very different scales. If we refer again to the sort of first link of the prediction chain in terms of what are the services for meteo and climate hazards, we usually have products that are global and that are issued and managed a global, national, down to the regional level. For example, in Tuscany, we have a regional level that issue meteo-based early warning. Then to bring the meteo warning in to a river flood warning, we have to work at the hydraulic scale, which is usually the basin scale, which is a smaller scale. Okay, this is here depicted in our testbed as the Arno River. This is about 1/3, 8,000 square kilometers, 1/3 of the Tuscany region. But if you want to push the early warning chain down to the impact, we have to work a much, much finer scale. Okay, so and for example, what I will address is very related to the goal of our UNESCO Chair. It's the target as a local impact is the Florence Historic Center, which is a UNESCO World Heritage. So this picture brings very clearly an overall concept that we have when we move to hazard toward vulnerabilities and impact, we have to move to very large scale to very local scale. And this is kind of not quite a trivial challenge to perform at an operational level. Okay, so this, for example, is what sort of the level of more consolidated research we are doing. The Tuscany region is actually running our operational flood prediction model. And this picture here with the picture of the basin on the left and the typical flood prediction, river flood prediction product on the right highlight a very, I would say, particular difficulties in issuing reliable flood prediction and the concept of uncertainty or probabilistic prediction, that such a small basin to have a usable early warning, you have to issue prediction not just based like this black part here on the bottom graph on measured rainfall, okay, but there is the need to use precipitation forecasts due to the very fast hydrologic response of the basin. And so you have a sort of propagation of the uncertainty of the meteorological quantitative precipitation forecast. These different colors refer to different rainfall prediction from different meteorological models that gives a cascade of uncertainty also in the prediction of the flood wave in the river basin. Okay. Of course, so also on this part, there is research ongoing, the research we are doing, more mature, but which is important to highlight that this is again the importance of the cascade of scale. The precipitation prediction, even if it's progressively improving in quality, is not enough to have a good flood prediction. This very simple graph, okay, this shows essentially sort of scatter, very high scatter points, is the amount of measure maximum discharge for rainfall events with different amounts, okay? So even if we are able to predict very accurately what will be, for example, the precipitation in the next 24 hours, there is still a long road to go to have a reliable prediction. There's still a lot of variance to be resolved, okay? So we have done some research, as I said, more mature now, to use a sort of data-driven approach that is used as most that you can have from observation in the ground and from satellite to improve the model accuracy and prediction capability in a general framework which is called variational assimilation. And our current research now is to use AI-based algorithm not to substitute the physical-based model, but to cooperate with the physical-based model to improve the understanding of the model error and hence to improve the accuracy of flood prediction. Okay, I will skip this is two-way detail. But again, the more, I would say, recent research we are doing, as I introduced before, is to push the early warning chain in assessing what is the real-time impact predictions. And so we have working a lot on what are our current operational and future operational flood damage estimation capabilities. And of course, we are testing this on damage on very different kinds of assets. Of course, which is the easier one, where we have more data in terms of vulnerability and exposure with economic estimation of possible impacts. But these are more or less the easy part. We don't expect too much to change this in real time in terms of exposure or vulnerability. What we expect to change much more, okay, in terms of exposure and vulnerability is, for example, impact to people. Okay? For example, it is current, I would say, experience that most of casualties during flood events, especially during flash flood events, is people in vehicles. Okay, so we are testing and building and testing some tools that at a very fine scale are able to predict what are the flood and flow velocity along the roads, and with some vulnerability model we established both on some theoretical and flume experiment, also to translate this, I would say, velocity and flood depth prediction in actual hazard to pedestrian and to vehicles, or which is more related to the overall, I would say, one of the main goals of the UNESCO Chair, that is the prediction of the cultural heritage. Also, what does it mean to have a real-time estimation of what would be the impact, for example, for our case study that I mentioned before, the Florence City Center UNESCO site, what will be the different impact that you may expect for different kind of historic building, churches, museums, and so forth. Down to the very, we say, utility for real time, for example, estimating how many emergency teams do you need to relocate in real time earthworks in different parts. Okay, so I will finish my presentation with this very last slides. I will give the floor to Chiara Arrighi, that we will go much deeper in the last things I've shown you about real time and in general community involvement in risk management for cultural heritage. Thank you for your attention. Let me, okay. And of course, we will have time for questions at the end if you have any.
Okay, so now it's my turn. Hello, everyone. I'm Chiara Arrighi. I'm sharing my screen. And now you should be able to see my presentation. Okay, so a little short introduction about myself. I am program coordinator of this UNESCO Chair, and I'm also assistant professor of hydrology at the Department of Civil and Environmental Engineering at the University of Florence. And my presentation follows the one previously given by Professor Castelli, especially related to some particular challenges in damage estimation and risk assessment for art cities. Of course, Professor Castelli already introduced the UNESCO site of Florence, and since we had some experience in these years about flood damage assessment, having some mature ideas led us to the idea of including community participation for risk assessment for this special case of art cities, and we will see in a while why this is required. So my presentation will be very short. It will be structured in some background and methods, some results, and some future outlooks. So we all know and probably enjoy for our vacations art cities because they are known for their rich cultural heritage, but we are aware that many of these historical cities have been founded near rivers or coasts because waterways are essential for trades, and these make them often exposed to flooding. And of course, historical and art cities have several buildings which can have several centuries and may host artworks which are especially vulnerable to natural disasters, and they can be also irreversibly damaged by water. And art cities obviously often rely heavily on cultural tourism, and damage to monuments or museums can have an effect on economic sustainability of art cities, but also can affect community cohesion and cities' identity. So my colleague have already introduced the concept of risk as a combination of hazard, vulnerability, and exposure. And I'm adding also capacity, which is something that was not explicitly said, but refers to the ability to face a disaster and to recover quickly, which is of course important for our cities and their livelihoods. So why cultural heritage is so complex in damage and risk assessment? So I'm switching a little bit to the part of impact analysis because values matter a lot in risk assessment, because the more valuable an item is, the more the impact we can expect. And for cultural asset, understanding values is particularly tricky with respect to other assets such as residential buildings or infrastructure, where easily we can identify replacement or renovation costs. Cultural assets are typically have two main values according to existing literature: the so-called use values and the non-use values. On the left of this diagram, you can see some example of use values, which are either extractive or non-extractive. The extractive ones refer to economic values, labor values, and income and revenues, which are clearly understandable for art cities and all the tourist activities. And these kind of values can be estimated somehow with econometric methods, such as hedonic pricing or willingness to travel, willingness to pay, and so on. So somehow, although it's quite complicated to define this value, there are some existing techniques to estimate this kind of values. On the other side, we have, unfortunately, the intangible sphere, which is as well an important component of value. In fact, the non-use values are referred to in spiritual, historical, social, symbolic, and many other values which are intangible and very hard to define. But we realize that the community is based on the cohesion and identity that cultural heritage provides. And we consider that in risk assessment, these intangible non-use values of cultural heritage should be included. So what we try to address in some recent research is to use participation of communities in order to merge two dimensions of risks which are typically separated, because normally, as also our colleague mentioned, we are mainly focusing on the physical dimension. So we are able to estimate event probability or magnitude for flooding, how frequently an area can be affected and which area can be flooded. We are quite good at estimating the physical exposure, how many buildings or how many residents. We are becoming quite good in assessing the physical impacts, but then we completely miss in this chain the social dimension. So how cultural heritage is valuable for the community. And that's why we wanted to do some research about understanding the intangible impacts by valuing one of the non-use values of cultural heritage, which is the social value. And to do that, we decided to use a participatory approach. And to be quantitative, because still we are disaster risk expert and we want to be quantitative, we decided to use a pairwise comparison approach for participation. This technique is widely used in decision making because it allows to compare two items at a time without assigning ranking to numerous items, and this is easier for our brains to make comparison of two elements at a time. And we also consider that the pairwise comparison approach administered to several members of the community succeeds in including all the voices of the members of the community with respect to other participatory approaches where people agree on what the majority decides. So we involved in Florence a local community of interest to make a test. And this local community was made of association of citizens, so residing in Florence, which are involved in the management of the UNESCO heritage sites. So they deal with cultural heritage, but they are not necessarily experts. They can be volunteers which participate to some cultural association for promoting the heritage in the city. And as I said, we use this pairwise comparison approach to estimate one of the many multiple non-use values of cultural heritage, which is the social value, which is defined as the value generated collectively within a community as a result of personal upbringing, personal life experience, relationship, communication, and travel. So a personal perception of value. In this image, you can see how we set up a survey, which was administered to our test community. And this pairwise comparison survey was developed ad hoc by our research team because there aren't any tools available on the market to make this kind of surveys, while others are more common. And this survey looks like this, with a general question that is repeated all the times. Which one would you recommend to a friend between two elements which are sorted by our algorithm based on Swiss tournament method, which maximizes participation and creates some combination between items which are having the same score? So for the people who are answering, they find on their device two elements and they have a description, the name of the elements and a picture. And then they can select in this pair the one that is preferred. So by collecting multiple replies, and we collected more than 2,000, then all these elements, based on how many times they won in the competition, they get a ranking. So let's see what were the results we obtained with this test of participation. We consider about 50 cultural heritage buildings in the UNESCO site of Florence. And what we found, this is the relative ranking of all the elements that we compare in the survey. We found that there is a good agreement that those buildings that already received the outstanding universal value attribution were the most important, also in the perception of the community. And in the second block, so those ranking high but not as high as outstanding universal value, we found mostly museums. And in the third block, we found mostly religious buildings. Of course, we have tried to interpret these results, but what we believe is that probably religious buildings are more related to the personal sphere rather than a social value for a community in general. But this is, of course, could be better interpreted. What we also found is that these values obtained by participation could not be estimated with other simple proxies, such as the number of visitors or the ticket price. We found that indeed the social value is correlated a little bit with the price of the ticket, meaning that higher value is attributed to those monuments or heritage attractions that have a higher admittance ticket, higher prices for admittance ticket. But we could not find very good correlation that allow us to estimate the social value with simple data. Of course, thanks to the use of geographic information system, we can also map these results of social value estimation in order to visualize in our area those resulting with a higher social value, which are those depicted in dark purple. And of course, having a georeference position, we can also intersect the spatial information about social value of cultural heritage with information about the hazard. In this case, we consider flood hazard. So in this map, we can see on the left a simulation that reproduces the last flood occurred in the city of Florence. This historical event occurred in 1966, and this reproduces the hydrologic event with the same discharges, with some changes made after the event in terms of mitigation measures, but you can still see that large part of the city is affected. This is the historical city center where the majority of cultural heritage building is. If we extract this physical characteristic, which is the water depth to the buildings we are investigating, we see that the larger water depths are corresponding to this cluster of buildings within the ellipse. And then the idea was, since we are aware that the depth, so that the magnitude of the flood is well correlated with the physical damage, so this is also a measure of the potential physical damage, what will happen if we weight this value by the social value, the one obtained by the community? If we do this in the third map, we can see what happens. It happens that, of course, we find back the same cluster of highly exposed cultural buildings with higher water depths close to the river. But if we also consider the social impact, we see that another cluster is appearing with cultural buildings which are far from the river and where we expect to have less severe inundation depths. But at the same time, since the social value is so high, in terms of priority, they come very close to those which are instead typically considered only based on the physical understanding of the phenomena. So this, as all the time that we consider participation, opens the way to some management or some prioritization of funding, also including the community perception. Of course, we are trying also to change the sample of community and see if these results can be sensitive to the type of community that is involved, that this will be led to future research. But after these years of experience in cultural heritage risk assessment for flooding, we realized that there is a limited understanding and awareness of cultural heritage managers that knows that they can be flooded, but they are not capable of identifying appropriate mitigation solution. So I would like to conclude with some future outlook about what's next in this context of research. What we are experimenting in order to make the flood risk perception easier for heritage managers is to move from the urban scale to the single building scale and try to simulate what will actually happen inside the building, because some of these buildings might have basements or underground floors, and so it's not easy to understand what happens to each single building with respect to an inundation scenario. And we are going in this direction in our research group also for pluvial flooding, not just for river flooding. So we have some experiments ongoing about understanding really what happens inside the building in order to better communicate to the decision maker and to cultural heritage managers. And to conclude, within European Ministry of University funded project, we are also experimenting building information modeling for cultural heritage, which is capable of visualizing the effect of river flood scenario within the building itself. So letting the heritage manager understand and visualize with augmented reality what can be its flood scenarios within its cultural building, and also having some rules and guidelines. In this case, on the right, you can see some colors that show where it's better to place some artworks vulnerable to water contact, such as painting. In this case, all the spaces are marked in red except this one in green, and this suggests to the heritage manager that this is the safest place where they can exhibit some materials like paper or canvas that could be potentially affected by flood. So we are going to the direction of helping heritage managers in their single flood risk mitigation at the building scale. Thank you for your attention. I will be here in case there are questions, and I will interrupt.
Thank you, Chiara,
the share.
Silvia, Fabio. So I'm asking if there are any questions now from the audience.
Hello. Hi, I have plenty of questions. First of all, thank you very much for the very interesting and overarching set of presentations. They are really very impressive work. Congratulations to all. I have a long list of questions, but I will try. It's just one per presentation, I think. So in the case of the landslides, I was wondering, how do you include in detail the vulnerability of the buildings and how that works with the evolving vulnerability of the slope? I think it's for Veronica, this one.
Yeah, yes. Yeah. Well, I went very fast about the vulnerability assessment, which is, I think, usually in the landslide vulnerability assessment is the weak point, because it's quite difficult to define vulnerability, because landslides are have a very high variability in terms of velocity, dimension, and so on. According to, we have tested several methods. According to the case study that I presented, MISA, we assess vulnerability combining the landslide intensity and the resistance, structural resistance, based on several parameters of the buildings within the census sections. You are from Italy, Dina, so you know the sections. And we derive parameter related to the state of maintenance, number of floors of building, and type of foundation. Then, using a literature approach, we define the structural resistance for the census section, okay? And then we combine.
Okay, so yes, large scale, in other words.
Yeah, large scale. So this is an application for large scale. Yeah.
And I think you gave, in your last slides, you gave a value of risk.
Yeah.
And I wonder, what is the return period for that?
Yeah, this is another weak point, because we could have a return period if you add hazard.
Yes.
Yeah, but it's quite difficult. Well, we are, for other case studies, we are working on defining different return period for landslides, because we should have temporal occurrence of landslides to define the return period, which is quite difficult to collect. Okay, so in these approaches, preliminary analysis, which we just use susceptibility, so it's a sort of static picture of risk, considering the activation of all the landslides in the catchment scale. For Italy, for example, we are collected, because we are working on also at the national scale, we are collecting information, because some regions have, some other not. So we are moving in that direction to assign a return period and to see how increasing the return period change the risk. Yeah.
Thank you. Thank you.
You touched the more, let's say, weak points of our analysis. We know, we are aware, and we are working.
No, well, they are not weak points. I mean, everybody's working on that. So yes, it's
yeah. Anyway, yeah.
Yes, landslides rarely occur for exactly
landslides.
the same point. So yes,
yeah.
Exactly. Thank you. And Fabio, I think in relation to the flooding, I have more or less the same question. How do you account for the vulnerability of individual buildings to flooding in your?
Yeah. That's a long path. Of course, there are some more or less standard vulnerability curves for different type of buildings. But of course, as for example, as we move to general house buildings, when we go to, for example, to cultural heritage, as Chiara was illustrating, now each building has to take into account its specificity. So it's really a long path. The general concept is that really there is a real need to move closer to smaller and smaller scale as we move from hazard to solutions. Okay, so there is a warning to the answering the question, what can I do as a citizen, as part of the community, as as a heritage building manager, and what can I do is becoming more and more important to be answered precisely. Okay, yes. So I guess most of the research, rather than providing vulnerability curve for different type of buildings, is mostly now shifting to, or at least we are doing it, is to construct methodologies, okay, to have a more precise estimation of what could be the damage for a specific building. Okay, we have been experiencing this, for example, in terms of seismic. We have in Italy, I guess, as in Japan, right? There are regulations to estimate what is the seismic vulnerability of each building. Okay.
Yes.
So we have some experience from other hazards on how to do that.
Yes.
Okay?
Just to point out that we, with my group, we have developed some of that vulnerability approach for historic masonry building affected by flooding. So it would be interesting.
Yeah, it would be very interesting to exchange.
Yes,
to
further discuss this. Yes, thank you. Thank you very much again for your presentations.
Thank you for your question.
If I may add something, Dina, to my answer, because I answer concerning the let's say regional catchment or national scale. We have also worked at local scale, taking into account just a single landslides, and we have done some research constructing fragility curves based on the deformation measurement from, for example, satellite data, as Silvia presented, or other type of. So it depends on the scale of work. Yeah, just to specify. Yes. Thanks again.
Thank you. Thank you.
Yeah, thank you very much. May I talk that I'm Tachikawa Researcher Wendy from Kyoto University. Thank you very much, Professor Fabio Castelli. I really think that you mentioned real-time impact predictions. That is really very much important. We are hydrologists, and we can predict river discharge in a real-time basis. And we talked that 1,000 cubic meter per second will come in next 5 hours. But most of the case, people don't understand what is a 1,000 cubic meter per second, which is dangerous and not dangerous. But I think really impact, real-time impact prediction is a really splendid, great idea. Thank you very much for that idea.
Thank you for your comment.
Yeah. And the last presentation, Professor Chiara Arrighi, I'm sorry that I'm not well pronounced. I had a very similar experience, not museum, but hospital. To design the hospital, emergency rooms usually are located in the first floor, and how in flood situations, hospital is very, very vulnerable and dangerous, and how to make design or the hospital manager can well understand how the water will come. I think your idea, 3D showing the water situation is really, I'm very much impressed. Thank you very much for great presentations. Thank you.
Thank you. Thank you very much for your comment.
Hi. I have a curiosity for all of us. First of all, my congratulations for the presentation, because I think that the three main elements, risk, early warning system monitoring, and scenario-based solution for the responders are the three pillars that we need to connect together. And this is the starting point for my curiosity. It's not a question. Did you work about the idea of related the use of risk mapping, your proposal, Veronica, in order to define the more the parts that require more attention in terms of monitoring, and then related this monitoring to to forecast the possible scenario that Fabio explained. So, because I think that there are all the elements that permit to close the chains that Fabio introduced. And it's very important also to help the last presentation, because the problem with the community is to show, I think, the final impact. No, Fabio, as you mentioned, what can happen if something happens. But the problem is at the beginning. In your risk map, do you take in account also the trigger events, means related the possibility to have the landslides and the typology of landslide to the different trigger events, heavy rain, earthquakes, or something like that, or is only a map derived from the GIS, like a characteristic of the geomorphological elements of the territory?
I start and then okay, concerning the map, risk map that I show was constructed starting from susceptibility, so spatial occurrence without taking into account the trigger elements. We are working also on other type of approaches, for example, physically based approaches for landslides, in which you can forecast the occurrence of landslides with different type of rainfall. Okay, so it depends on the model we are using, but in the case that I show was just simple a spatial prediction without taking into account the trigger, so which could be rainfall or earthquake. As I explained before, we are trying to move to more an hazard assessment, so take into account, but it depends on the scale of work. It's more simple for small areas in which we can use physically based approach for landslides and collecting all the necessary input data, which are geotechnical and hydrological. It's more difficult for very large scale, in which to have an hazard assessment or consider the trigger is more difficult. So our aim with providing this very large area risk map is to identify areas in which then you have to apply further more accurate with a different type of approach. I think is just to prioritize also the intervention in terms of monitoring system and other type of evaluation.
I agree. It's a parallelism, but as Fabio mentioned before, you are able to be precise at local scale, but in the same time you need a sort of layer approach of planning from big scale, medium scale, and local scale. But it's very important because define the priorities where you have to, especially if you have not enough resources to to focalize the attention. Thank you so much. And another question to Fabio. It's very interesting, the data-driven approach related also to the forecast for the future in close time. About this, do you think that it's possible to create something in the future? You mentioned the artificial intelligence, but like to create a sort of database of events in the area with a description. Do you think that this can help the process jointly with the models, obviously?
Yes, of course. Okay. The data-driven approach doesn't mean that you have to substitute completely the model with the data, okay? Mm-hmm. You have to build synergy with that. Okay, so as you push further the prediction chain, you are able to get more and more data to assimilate in the modeling. Okay, so if my prediction chain is able to arrive to the real-time prediction of the impact, I can use impact data to improve backward also the flood prediction. Yes. And also, so we are experimenting this now at the level of using, for example, satellite estimate of inundated area.
Yes.
Okay. Yes. Not right at the impact, but at least at the inundation. Yes, we have a few papers on that.
Okay. Thank you so much.
I think there is another question from Aldo Primiero.
Hello, I'm Aldo Primiero from Civil Protection, Friuli-Venezia Giulia. I thank you for your presentation. I have a question about the cultural heritage protection, because in our also in our emergency plans we map the buildings and also the content of the buildings, and so I was interested in understanding if there is a methodology also to evaluate the vulnerability or the resilience of the single building that is a container for the cultural heritage? Because I know in some museum they make some protection, like for both for maybe for risk of floods, but also for seismic risk. And so they if they protect the container, also the content is more protected. But okay, there are some artwork that are more resilient to floods, and other no, books or statue or other things. And so I want to know if going in detail of the single building, you also can evaluate this aspect.
Yes, thank you for your question. Well, indeed, we have several research lines, and one is exactly about developing vulnerability function for specific buildings, so focusing on the two parts, on the building envelope, based on the characteristics of the envelope, so the presence of underground floors, the elevation of the ground floor, which can be for the case of churches, for instance, maybe 1 meter or more with respect to the road level. And on the second part, the content, so the artworks which are included. And we collected to develop these vulnerability functions all the billing prices of the art conservators and renovators that worked after the 1966 flood, to understand which kind of operations are undertaken to restore paintings or sculptures or painting on canvas after a flooding. And we are, after having the operations, we can retrieve the cost, the current cost of the same operations. And in this way, we can also estimate for different water levels inside the buildings, the elements, the artworks which are exposed, and their restoration value. So we are also working in this kind of vulnerability, asset-specific vulnerabilities for envelope and artworks. And beside that, we also had an analysis again at the UNESCO site of Florence, to understand how many heritage managers are aware of the risk of flooding they are facing, and how many of them are currently finding some local mitigation strategies. And only 3 buildings which are the closest to the Arno River, since probably they are quite well aware, they see the river every day, they undertook some mitigation measures. For the case of the National Library, they decide to move their collection, so the most ancient manuscripts from the 15th century are on the upper floors, and they put in the lower floors the less important collection, for instance. And some others are experiencing and testing some lifting mechanism for large paintings, which can be automatically activated in case of a warning, and that they lift up these large paintings that are not easily moved by people, because they are really huge in terms of size. So we are also working on this. But of course, the warning, the phase of the warning, so the actions that can be undertaken during the emergency phase need still to be considered by most of the managers of cultural heritage, because in case of warning, most of them are not fully aware of what to do. So some of them made some plans to mitigate the impacts. Some others didn't make any of these mitigation measures and are not fully aware of what to do and how much time they have to take actions during flood warning.
Okay, thank you. I think the BEAM approach could have a good
yes.
future.
I think that
Yeah.
BIM approach will force people to visualize their situation, and they will they motivate many people to take some action. Yes.
Thanks. So if there are no other questions, I think we can conclude now the seminar.
Sorry,
You have.
if I can, I have another
sure.
question. For Chiara, I think the idea of the pair comparison was, it's a great idea. And I would like to understand what do you think is the bias that you have in the result, considering that the main monuments and buildings, they might strike higher social impact just because they are better known than the other one, rather than that because people really enjoy more or value them more.
Yeah, this is the reason why for this first testing of the procedure, we wanted to have a control community which knows quite well the situation of the historical city center, and not just common citizen that might have maybe a limited knowledge of some particular building. So we selected this control community because they are not necessarily experts, but they are aware of what is inside the UNESCO site because they contribute to activities or promotion of cultural heritage. Of course, when we consider the opinion and the perception of the single people, we bring into the results the preferences and the bias of the community. And of course, this kind of results might change in time, because if you repeat the same experiment in 10 years, maybe you get different results because the community has evolved their perception. But what we believe is that if we are able to involve a large amount of people and collect a lot of answers in terms of citizens, we can maybe, since each one expresses his opinion, we can try to figure out that each one has its own bias, but at the community level, we get some results which we think are reliable. Of course, it's a matter of involving a larger amount of people, which so far, for technical reasons, we were not able to do. And the other aspect is that we would expect quite different results if we are involving the locals and if we are involving the tourists, because we have 10 million tourists that visit Florence each year. So this would be nice to understand if there is a spread between these two perceptions.
So I wonder whether you can have an app that is connected to the UNESCO World Heritage site that basically that runs your same analysis.
It would be,
for anybody that comes and visit. Once they buy a ticket, then they have.
We are currently searching funding for that.
We are
good.
Searching funding.
Yes. I think it would be a very good. Well, maybe you should ask UNESCO.
Yeah.
Good. Thank you very much for the answer.
Thanks for all the question. What? Are there any questions? So maybe we now can conclude, really?
So, Veronica, if I may, just to not to with other questions, but to conclude, I will thank you all of you for these very interesting presentations, really for touching these interesting points and for fostering this discussion that was really interesting for everyone, I think. And I invite you to follow our Resilience webpage as well as our media in order to stay in touch also for the future coming Resilience talks. So many thanks to all of you for having it and for this meeting of today. Thank you so much.
Thank you. Bye-bye.
Bye.
Bye-bye.
Goodbye.